Welcome. In this video, we will examine the application of linear programming in business decision-making through three fundamental methods: the primal simplex method, the method with artificial variables, and the dual simplex method. Each exercise focuses on a real scenario for American Factory, optimizing the allocation of resources for different products. Technological optimization tools were employed. Solver was used in all exercises, QM complemented the analysis in the second exercise, and a specialized application was used for validation in the third exercise to confirm the optimal solution. Let us begin the analysis. Exercise 1, Primal Simplex Method, Problem Statement, and Mathematical Formulation. American Factory is engaged in the production of food pasta. The linear programming model aims to maximize the profit derived from production, subject to constraints related to the availability of inputs and the plant's operational capacity. Objective function. It is expressed mathematically in terms of decision variables with coefficients representing the contribution of each product to the total profit. Constraints. Linear equations are established that limit the consumption of raw materials and other critical resources. Algorithm development. The primal simplex method transforms the model into its canonical form. An initial simplex tableau is constructed where the most critical negative coefficients are identified to select the entering variable, and the leaving variable is determined using the strictly positive minimum ratio criterion. With each iteration, the tableau is updated until optimality is reached, ensuring that all coefficients associated with non-basic variables indicate that the objective function cannot be further increased. Results analysis. Mathematical analysis confirms that the final solution meets all constraints with equality, which guarantees the feasibility of the model. A sensitivity evaluation is conducted to assess the impact of small variations in the parameters, thereby verifying the robustness of the optimal solution. In this exercise, validation was performed using Solver, which corroborated the precision of the iterative process. Exercise 2, Method with Artificial Variables, Problem Statement and Resolution Strategy. In this exercise, American Factory produces MDF panels. The model presents constraints that prevent obtaining a feasible initial solution directly. Problem setup. The original formulation requires the incorporation of artificial variables to achieve an initial basis. Resolution strategy. A two-phase method is used. During phase 1, the sum of the artificial variables is minimized to obtain a feasible solution. Subsequently, in phase 2, the original objective function is reinstated and maximized. Process development. In phase 1, the objective function is modified to penalize the artificial variables, and the simplex method is applied until these variables are eliminated, reaching 0. Once feasibility is achieved, phase 2 resumes with the original objective function, and iterative adjustments refine the optimal solution. Results analysis. Mathematical analysis confirms that after the elimination of the artificial variables, the final solution is both feasible and optimal within the solution space. The model's stability is evaluated through a sensitivity study that demonstrates how the solution responds to changes in the coefficients. In this exercise, in addition to Solver, QM was employed to provide a deeper quantitative analysis and validate the accuracy of the method. Exercise 3, Dual Simplex Method, Problem Statement, and Dual Transformation. This exercise focuses on the production of sanitary porcelain at American Factory, with the objective of minimizing production costs. Since the primal formulation presents difficulties in obtaining a direct solution, the dual approach is adopted. Dual transformation. The dual formulation reverses the roles of the constraints and the variables, allowing the coefficients to be interpreted in terms of shadow prices and evaluating each resource's contribution to cost minimization. Dual algorithm development. The original model is restructured, generating a new initial tableau where the objective function coefficients and constraints are reinterpreted according to the dual approach. The dual simplex method is applied iteratively by updating the basis and adjusting the coefficients until optimality is reached. Each iteration facilitates the economic interpretation of the shadow prices associated with each resource. Results analysis, mathematical analysis demonstrates that the optimal solution obtained via the dual method is consistent with that of the primal model, thereby validating the duality principle in linear programming. The interpretation of the shadow prices highlights the critical resources and allows an evaluation of the model's sensitivity to parameter variations. In this exercise, validation was carried out using a specialized application which confirmed the consistency and robustness of the dual solution. In summary, this video has presented a technical analysis of 3 linear programming approaches applied to real scenarios at American Factory. The Primal Simplex method optimizes profit in the production of food pasta while meeting resource constraints. The method with artificial variables enables the resolution of models lacking an immediate feasible solution, as applied to MDF panel production, with QM complementing the quantitative analysis. The dual simplex method is used for cost minimization in the production of sanitary porcelain, facilitating the interpretation of shadow prices and model sensitivity through a specialized application. The mathematical results, verified using Solver, QM, and the specialized application, confirm the validity and robustness of each approach, providing a solid foundation for strategic decision-making in industrial environments. Thank you for joining us. We remain available for further exploration of these methods and their real-world applications.